Hello everyone. We continue our discussion of p-n junction formation. So we learn, like short recall, to be on the same page, that when we put two semiconductors together with different types of conductivity, there is diffusion of majority charge carriers and drift of minority charge carriers. Drift because during diffusion we form certain space charges at the interface, positive charges from n-type and negative charges from p-type. These charges are formed by immobilized charges like ions of donor and acceptor centers with which we dope the material. So these space charges obviously create internal electric field, and this electric field forms, first of all, potential, because of electrostatic potential distribution. It forms a potential barrier for diffusion of majority charge carriers and enhances drift of minority charge carriers. These fluxes of charge carriers compensate each other, and eventually we have equilibrium condition. So we went into details and tried to understand what will be profile. So as you see here on this image, like in this part, we have step-like profile for space charge, considering uniform distribution of acceptor and donor centers. And as a result, according to Poisson's equation, relationship between first derivative of electric field and space charge, we can calculate by integrating Poisson's equation for left and right side for p and n type distributions of electrostatic field inside these depletion regions where space charges are located. Depletion regions means they are depleted by majority charge carriers, and they possess much higher resistance in comparison to neutral regions, like here, where there is no electrostatic field and no space charge. So we did this integration. We got two equations for electric field distribution for p-type region, like depletion region, and n-type depletion region. And assuming that, so there are some linear functions, so we see at this part of the plot, and they increase from 0, go to some maximum value at the interface, like where n and p-type are in contact. And because there is no discontinuity between electric field, we should have a condition when electric field from the p-type semiconductor should be equal to that one at the n-type. Okay. And from left and right side, so they should be the same at the interface. And we highlighted this feature, so assuming that x is equal to 0, when we substitute to these equations, x equal to 0, and we get this relationship between the product of acceptor concentration and width of the depletion region in p-type and donor concentration width of the depletion region in n-type. So if we increase one or another, like doping concentration of acceptors or donors, that will result in increase or decrease of depletion region. So that we discussed in details last time. That's where we started, finished last time. And now, obviously, when we have electric field distribution, electrostatic field distribution inside the depletion region, we want to make next step and determine electrostatic potential distribution. So we can do this because obviously there is a relationship between electric field and electrostatic potential. So we need to integrate our expressions for electric field distribution once more over position over axis x, considering this boundary conditions. So if we start from minus WP, so it's left edge of the depletion region in p-type semiconductor. So we said, because it's always arbitrary parameter, electrostatic potential, we need to set something to 0. So we set this to 0, and then as a result, potential difference between this edge and this edge should be VBI, built-in potential, which corresponds to the height of the potential barrier, which is Q times VBI. So considering these two boundary conditions, we can do our calculations. So let's do it first for p-type. We have this function of electric field versus position, and we can write that that this is equal to negative first derivative of electrostatic potential over position x. So we derived it during our previous lecture. So now we need to integrate it over position x in order to get this electrostatic potential as a function of x. So we get two integrals here, and once we integrate, we get this constant C3. So we determine this constant with our boundary condition for the edge of depletion region in the p-type semiconductor. Considering that it's equal to 0, then we substitute, instead of x w minus wp, we can finally extract this, express from this equation value for our constant, and once we know this value, we can substitute it in first equation, which gives us the electrostatic potential as a function of position x. So by substituting it here, we get the final expression here, and after some rearrangement, we can get the in most convenient form this solution for electrostatic potential distribution over position. So we see here that it is x in second power, so it's quadratic distribution. We had linear distribution for electric field. Obviously, when we get one more integration, we get quadratic square dependence. So similar procedure should be done for electrostatic potential distribution in the depletion region of n-type semiconductor. So we also integrate this expression for electrostatic field, get constant C4. Now our boundary condition is different. At the edge of the n-type semiconductor depletion region, this boundary condition is equal to VBI. So we put it here, VBI, and instead of x, we put WN. So we get the expression for our constant C4, substituted here, and finally get also expression for electrostatic potential distribution in the n-type depletion region of the semiconductor of this PN junction. So we have these expressions. Let us then come back and see. So these are the equations which we derive for electrostatic potential distribution in N and P type, like P and N type regions, depletion regions. So now take a look here at this part of the figure. We have graphical representation of this quadratic distribution of electrostatic potential. So we have certain potential difference, like between the edge of the depletion region in the p-type and interface. So this is V P, and also between interface and edge of the depletion region in the N-type semiconductor. So this is Vn. Obviously that we can determine quantitatively their magnitudes, so we can just substitute in these equations positions. For here we can put minus Wp. Here we can put Wn. Okay, so that is a mistake. Should be N. Wn instead of X, and we can get the maximum potential difference in this scope of the depletion region in the p-type and n-type, so this Vp and Vn. Obviously, the total potential difference over the p-n junction will be Vbi, and that is equal to the sum of these contributions from each side of the p-n junction. So that what actually matters, sorry, because Vbi defines the height of the potential barrier. So now when we have based on this step function electric space charge distribution, we have electric field distribution and electrostatic potential distribution. Obviously, our next step, we can draw the correct band diagram of a p-n junction. So this will look like shown here in the bottom of this figure. So this part. First of all, we need to highlight that band diagram is drawing for electrons. Electrons are negatively charged, so we have this minus Q. So we need to, when we go from electrostatic potential to energy, we multiply electrostatic potential by negative charge Q, elementary charge of electrons. That's why it's kind of mirror reflection of energy, like of band bending is a mirror reflection of electrostatic potential distribution. And we have now this energy diagram, which you have seen before. You just now step by step from this graphic also it's quite obvious, and also from analytical point of view came to this point when we understand why energy diagram of a p-n junction looks like this and not in a different way. So what is important here is the total width of the depletion region. So depletion region means that I generalize it and include both sides, N-type semiconductor side and P-type semiconductor side. However, from practical point of view, what we can further measure, and we will see what kind of parameter depends on it, that is total thickness of the depletion region. And that would be quite useful to derive some equation which can give us an option to calculate this width. So let us take a look on these two equations which we derived for electrostatic potential distribution. So here should be N. Pay attention on this point here in the middle of the p-n junction at the interface. So since we have no discontinuity of electric field at the interface, we also don't have any discontinuity of electrostatic potential. So it goes smoothly from N-type to P-type semiconductor. Since that is the case, we can substitute here instead of x 0 position in order to determine with both of these equations electrostatic potential right at the interface. So that's what done here. From this equation we can express VBI in terms of thickness of depletion regions in p-type, in n-type, and also concentration of acceptors and donors. Okay, so but again I remind you our goal is to get the total thickness of the depletion region because that's like practically relevant parameter. So now we recall from previous slides we got this relationship which has shows direct relationship between concentration of either donors or acceptors and respective thickness of the depletion region, and the fact, quite obvious, that total width of the depletion region is the sum of widths of each regions. So now we, based on that, we can express WP and WN in terms of W. So that's what we want, and substitute it in here. So eventually we will have equation of VBI, not in terms of these two components, WN and WP, but in terms of W total thickness of the depletion region. So that's what we get here after substituting these two equations in previous. And now we can express W from this equation, the thickness of the depletion region, this part, sorry, it doesn't write, in terms of concentration of donors and acceptors, so there is some ratio between them, and VBI. So all other are just some constants and the electric constant of the material, epsilon.
I thought the equation will be squared because WP was squared.
Which equation?
The VBI. If you put WP, which is ND, W over NA plus ND into the equation 1.14.
Mm-hmm.
And then
To VBI, right?
we have
Yes.
ND square over NA plus ND onto the square. Back.
Mm-hmm. Yeah, so we get this W in square, and then we get like express W in square root of this from this equation.
Yeah, so
Yeah.
this is supposed to be.
Mm-hmm.
And then NA could come out.
Mm-hmm. Okay, so we now we know how important parameter of a p-n junction, total width of the depletion region, depends on the doping concentrations and building potential. However, now we see that it doesn't help us much now when we have this so-called symmetric p-n junction or close to symmetric, because it has two parameters, NA times ND divided by NA plus ND divided by NA times ND. So we need to know both, or at least one, so we can, by measuring the thickness of the depletion region, can determine unknown one. However, that is mostly not the case, and when you want to learn something about semiconductor, you would like to have so-called asymmetric p-n junction. So what does it mean, asymmetric p-n junction? So initially, all our discussion, we considered that concentration of acceptors and donors is equal. So then it's called symmetric because the thicknesses of depletion regions in N and P type semiconductor are the same. However, what will happen if one of the, let's say, concentration of acceptors will be much higher than concentration of donors? then obviously there will be discrepancy in these thicknesses. And if Na is much larger than Nd, then we can neglect with Nd here in the numerator and transform this equation for the thickness of the depletion region to a simpler form, where we have just concentration of some concentration N, this one, and that will stand for the lowest concentration of acceptors or donors, depends what. In our example, that was concentration of donors, because concentration of acceptors is much higher. So the lowest will be there in the denominator. So such a asymmetric p-n junction will look like this. So we have very thin depletion region in heavily doped p-type semiconductor, where Na is much larger than Nd, and that's one. We have much larger depletion region in moderately doped N-type semiconductor. So, taking this into account, the total width of the depletion region will be almost equal to the depletion region located exclusively in the N-type semiconductor, like N-type side of a p-n junction. And this equation will help us to determine this width of the depletion region. So once we have this asymmetric p-n junction with depletion region almost fully concentrated here in the N-type semiconductor, so this is the equation. Now we see that epsilon, the electric constant, and N concentration, in this case of donors, these are parameters which you cannot change. So you made the material, it possesses certain dielectric constant and certain concentration of donors. So what is the option to change the thickness of this depletion region? Here is this potential difference, which is like built-in voltage, VBI. How we can manipulate it? We can probably apply some external bias. So now your suggestions, what will happen if we apply some external potential difference to such p-n junction? So keep in mind we have here some internal electric field which is oriented from N-type to P-type. This electric field responsible for electrostatic potential distribution and means for this built-in voltage. To make it easier for you, we should consider different polarities, obviously, because we can either enhance internal electric field by applying external bias or decrease it. So let us see what will happen when we apply negative potential to the N-type semiconductor. So negative potential means that we apply positive potential to P-type. So external electric field, in this case, will be oriented from left to right. It goes always from plus to minus. That means that external electric field will reduce internal electric field, as shown here. We subtract internal minus external electric field, and as a result, there will be smaller electric field. Smaller electric field does not come by itself. It should be provided by certain space charge. And if initially we had larger electric field, this larger electric field required larger space charge in order to provide it. Once we applied external electric field, which reduced internal electric field, now it's smaller, so we also need smaller space charge. Since the concentration of donors, like ionized donors, these guys, is fixed, how can we change the space charge? We can only change its width. We can only change the volume this depletion region occupies, and that volume times concentration of ionized donors will give us the space charge. So that means that when we apply this negative potential to n-type semiconductor, positive as a result to p-type, we are talking about so-called forward bias in the forward direction. When we reduce potential difference, because we have here VBI minus V, minus applied potential difference to these electrodes, and as a result we get smaller thickness of the depletion region. So it shrinks, it becomes smaller. Since so here I would like to highlight again the fact that depletion region is depleted by majority charge carriers, means its resistance is much higher than resistance of these neutral regions. I mean, you can neglect with this guy because it's heavily doped, so it's very conductive. So you focus only here now. Resistance of the depletion region is much smaller, means that the total resistance of the p-n junction will be actually determined by this depletion region. And now you see, you go from case when you don't apply any potential, when you apply forward bias, the thickness of this depletion region reduced, means the resistance of the p-n junction also was reduced. And here we don't get any, so we consider in this equation, this V applied bias, that all bias is dropped over the p-n junction, over the depletion region. So that suggestion is quite reasonable, because for majority of semiconductor devices, the neutral region here is quite conductive in comparison to depletion region, obviously, and since we have kind of two resistors connected in series, so this is a resistor corresponds to resistance of the depletion layer, let's say, and this is resistor will be this will be a neutral layer. So our depletion layer is much larger than our neutral layer, and that's why all potential, external potential difference which we apply will drop over the depletion layer. So that what happens when we have forward bias. Now let's consider what will happen when we switch the polarity. So we go already for positive potential applied to the n-type semiconductor. In this case, external electric field will be oriented in the same direction as internal here electric field. It means we will just add up two electric field vectors and get the resultant larger electric field. So when we have so-called reverse bias, which stands for positive potential applied to n-type semiconductor in p-n junction, electric field internal increases. This electric field should be provided by larger space charge, and this larger space charge is resulted from wider depletion region. So means now when we apply reverse bias, we increase potential barrier, like built-in voltage, by applied external bias, and also we increase width of the depletion region. So that is the explanation of this depletion region dependence, like its width dependence on external bias applied to a p-n junction. Now look at these three images of like p-n junction structure. Keep in mind that we have here a region with very high conductivity. Here we have region with high conductivity, and in this area we have region with very low conductivity. Does it recall you something from electricity? No, transistor, that would be too advanced because we need to have one more p-n junction. Yeah, but easier, don't go so far. Just general electricity course. Which kind of electric circuit elements we operate? Huh? LEDs. No, LEDs, that's also p-n junction, which... Oh, capacitor. You're absolutely right. We have resistor, capacitor, and inductor in general electricity, what we discussed course. And what is capacitor? These are two plates, two metals, means conductive, very conductive materials, and in between we have some dielectric material with very low conductivity or high resistance. So that is actually a capacitor, but as opposite to a parallel plate capacitor, which you commonly deal with, one of the key parameters, the thickness of the capacitor, is not constant here, because as you see, the thickness of this depletion region, means region with high electrical resistance, is bias dependent. So we can manipulate with the thickness of this p-n junction capacitor, and by applying external bias, we will change the properties of this capacitor, which opens quite interesting opportunities for practical applications in different fields. So what will be capacitance of this, let's say, CD, let's call it like diode capacitance or barrier capacitance could be. Like capacitance, geometric capacitance of this depletion region. So we need to highlight this. So that is CD. So that will be, according to equation for parallel plate capacitor, the electric constant epsilon times epsilon naught, permittivity of free space, divided by thickness of the capacitor. And here, instead of like thickness of the capacitor, we use thickness of the depletion region, which is the function, like a function of applied external bias. We know how external bias changes thickness of the depletion region, so we know this function. If we have forward bias, then we consider this V as positive, so that's why we subtract it from VBI. If we apply reverse bias, this V we consider as negative, and that's why we add this V to the VBI. So now when we substitute, instead of W as a function of V actually function, we can get the expression for the depletion layer capacitance as a function of applied bias. So it will be Q times epsilon epsilon naught times n concentration of charge carriers divided by 2 times VBI minus V. So now we have a device which possesses certain capacitance as a function of applied bias. So we can manipulate with this. So as you see from here, that's important to underline. We will discuss this in details, of course, rectifying properties like JV characteristics of a PN junction. But besides that, besides the fact that diode can, like PN junction and diode based on PN junction as a device, is applied to rectify electrical current, so it possesses different conductivities at different polarities. It also can be applied as variable capacitor. So now let us consider this some kind of discrepancy which could be on intuitive level. So we claim that capacitance of this depletion region is defined by equation which is derived for parallel plate capacitor. However, there is an important difference between parallel plate capacitor and PN junction. So what do we have at parallel plate capacitor? So here is this dielectric with high electrical resistance, which is similar to depletion region in terms of electrical conductivity. However, electrical charges are strictly defined in space on the surface of these plates. So it is very thin surface area of plates of the capacitor where we accumulate electrical charges. That's not the case in PN junction, in the depletion region of the PN junction, because in PN junction we have space charge, and space charge is distributed. So we have negative electric charge distributed here, positive electric charge distributed here. So actually whole volume is the electric charge which is there. However, in parallel plate capacitor, all volume is electrically neutral, and electrical charges only accumulate, like reside on the plates of the capacitor. So what is important to highlight here? Why they are eventually behaving similarly. It's important to understand that when we apply some AC voltage, that's when we deal with capacitance, when we have AC voltage, because DC is kind of useless. It doesn't conduct DC current capacitor. But it is interesting to apply in AC electrical circuits. So when we apply some small amplitude AC signal, this small amplitude, let's consider it goes from so this is voltage, this will be time, and this is our AC signal. So it goes from 0 to some V maximum, some amplitude. So this change of potential difference at the terminals of the capacitor will cause some change. So if we consider dV as change of the potential difference, this will result in some change of electric charge accumulated at the plates of the parallel capacitor. And they are kind of localized in very thin layer at the interfaces. What will happen with PN junction? When we apply some AC voltage, we need to understand how we get these charges. So we also, some small change in potential difference of AC signal will result in small change of electric charges. But important thing that where they come from. So we can change electric charges in the depletion region only by changing its width. So means that at zero potential it was at this position, at some higher potential it became which corresponds to reverse bias polarity, it increased. So change of this electric charge is also concentrated in a quite narrow layer inside PN junction, which is defined by the change of the depletion layer thickness in the p-type, and the same should be in order to have electrical neutrality in the n-type semiconductor. That's why we can have an analogy between PN junction capacitance behavior and parallel plate capacitor behavior, because this small change of charges, which actually matters in terms of measuring capacitance, because capacitance is equal to Q divided by V, or in our case it could be as delta Q divided by delta V. So this change of charge, electric charge, associated with the charging and discharging PN junction capacitor and parallel plate capacitor will happen within these narrow layers at the edges of the PN junction. And that will be similar to accumulating electrical charges just in a thin layer on the surface of metal plates of the parallel plate capacitor. So that's why this equation indeed works for both, for parallel plate capacitor and PN junction. So now you may also ask why we care so much about this depletion layer capacitance. That makes a lot of sense to take an advantage of this feature of PN junction. First of all, it's used in many electrical filters, like RC circuits, where you can adjust capacitance, because this parameter could be kind of adjustable. So it's so-called Varia cup device, and it's a PN junction where you can, by applying external bias, change quite a lot. So it's designed in that way, is quite low concentration of donors or acceptors, that that the thickness of the depletion layer can change quite a lot with applied bias. Means in a quite wide range you can tune this capacitor without mechanical, like moving some plates in between each other. So it can be integrated in electrical circuits, can be quite small in size. It could be integrated into even microchips, and on digital level, applying some signals, we can manipulate targetedly the bandwidths of certain electrical filters in order to fine-tune these circuits to work at different frequencies. So, and that can be done by just applying some potential difference between electrodes of this Varia cup device, which is actually a PN junction made in order to have large change of thickness and its capacitance and thickness of the depletion region with quite low concentration of doping centers. And besides this practical application in electrical circuits, we also care a lot about depletion region from scientific point of view for analysis of materials properties. And that is so-called capacitance voltage characteristic when we measure capacitance of a p-n junction at different bias and plot this so-called Mott-Schottky analysis, which allows us to determine built-in voltage, VBI, and also concentration of doping centers. So here we have equation for depletion layer capacitance of the p-n junction, of asymmetrical p-n junction, when we have one side heavily doped, another is possesses much lower doping concentration. From here we can write the following equation. It will be 1 over CD square equal to 2 divided by Q epsilon epsilon naught times N, and everything times N VBI minus V. So you can see that 1 over CD square, this part, is a linear function of applied bias. So now if we plot, so this is Mott-Schottky plot. So we get some experimental data. We measure capacitance at different external bias. Then we plot 1 over CD square versus bias applied to our device, and we get linear function. So here in this region we have some deviation from linear behavior. That is because of so-called diffusion capacitance associated with injected charge carriers at forward bias. So we kind of inject charge carriers and then extract them. That is associated with some change of electric charge, because we add and then take it away. If we have some processes that because of changing voltage we change electric charge, it automatically behaves as a capacitor. However, it's not the electric capacitance of the depletion region. That's why we don't consider it right now here. So we consider only depletion, the electric geometric capacitance of the depletion region, which is associated with this Maxwell displacement current. So now you can see, if we extrapolate this linear dependence towards interception with the axis x, with the voltage axis, we will get VBI, because if 1 over CD square goes to 0, which is here at this interception point, then this expression in the parentheses should be also 0. Means that this interception point should be our VBI. So that is easy and straightforward way to determine built-in voltage in a p-n junction, which is, by the way, there are not so many options to do it with such accuracy as Mott-Schottky analysis. You can estimate it from current voltage characteristics, but this is direct way to measure it. And also, what is very important, we can determine concentration of doping centers in our material. Assume that you have some material with unknown properties, so you don't know how many of added impurities actually became electrically active and contribute indeed to doping. So you need to measure so-called doping efficiency, the ratio between added doping centers and actually the concentration of those centers which are ionized and contribute to actual doping. So from this equation we can see that from the slope of this linear dependence the ratio of change delta 1 over CD square to delta V, we can calculate the concentration of doping centers, which is indeed very important parameter and defines a lot of properties of semiconductor materials. So now we know how we can use for practical applications and also for research purposes depletion capacitance capacitance of the depletion region of a p-n junction. However, in order to use it, we need to know how correctly to measure it. So the question is how we correctly measure depletion capacitance in order to get really capacitance of the depletion region, but not some artifact. And that what many people kind of don't pay enough attention in research community, and that results in misinterpretation of experimental data. So I believe that is very essential moment, because it's good if you understand the origin of depletion capacitance in p-n junction. However, if you don't know how to measure it, you will not take any advantage of it. So let us consider this p-n junction with depletion region. So this is our depletion region, and the equivalent circuit of such a system, ideal case, should be some resistance, because it's high resistance, but it's still not infinity, so it still can conduct electricity, connected in parallel to our depletion layer capacitor. So that is ideal equivalent circuit. And so-called admittance, which is reverse to impedance. Impedance is the total opposition of electric circuit to AC current. So admittance is 1 over impedance, but we will show it again. It consists of real and imaginary components. So we have conduction and susceptance. So that is real part conduction and imaginary part susceptance. So conduction is just 1 over R, so reciprocal to resistance. And susceptance is determined by reactive resistance, which is impedance has this reactive component, which is imaginary part of impedance. But here it's flipped over also, because reactance of a capacitive reactance is, let's say, XC is equal to 1 over omega C. And susceptance is 1 over, as similar as conduction is 1 over resistance. So it's I times omega times C. So where I is square root of minus 1. So it's just the way how we show complex numbers. So now if we get this susceptance, we can easily determine capacitance. We just need to divide susceptance by the frequency of AC signal at which we measure this susceptance. Obviously, it will be a frequency dependent parameter. Everything easy peasy, but the problem is that in real life we need to consider a little bit more complicated equivalent circuit. So instead of just this depletion layer capacitor and depletion layer resistors, which is connected in parallel, we have also some series resistance. As I said, neutral region of this semiconductor is much more conductive than depletion region. However, it possesses small, but still it's there. This series resistance is still there. Plus, we have some electrical contacts to these devices. And these electrical contacts at the interfaces, they can also provide some additional resistance. Depends what the quality of this electrical contact. It can be very small or it can be quite significant. So in total, we have, instead of this ideal case, we have in addition this series resistance. So now let us consider impedance of this electrical circuit. It's quite simple electrical circuit, just two resistors and one capacitor. So we have, as I said, real and imaginary components. Real is this is active resistance, and imaginary this is reactive resistance. So we can do calculations, but like here is the already result. It will just take some time. So we see that there are two terms originated from series resistance and this combination of capacitor and resistor in parallel to the real components. So this is Z prime. And also we have one component originated from resistor and capacitor in parallel to the imaginary part of impedance. So now let us take a look how this frequency dependence of real and imaginary parts of impedance look. So I did this simulation for 5 nanofarads for the depletion layer capacitance, 5 mega ohms for depletion layer resistance, and 100 ohms for series resistance. You see that 5 mega ohms and 100 ohms, it's just 4 orders of magnitude difference. So indeed, it's way more conductive, but still not zero. So here, let's take a look on this black line. That is our real part, like Z prime, this guy of impedance. So it goes from saturation at high frequency, where we have the sum of, it's saturation at low frequency. So we go from low frequency to high frequency here. So saturation at low frequency, when we have the sum of depletion layer resistance plus series resistance. Obviously, this is huge number. It will be determined by depletion layer resistance, and we can, with high level of accuracy, just neglect with contribution of series resistance to low frequency real component of impedance. However, as we increase frequency, go to high frequency region, we get this second saturation regime. And here it will give us only series resistance. So without series resistance, it would just continue going here like this, down. But with series resistance, it saturates, and we can actually, from this plot, already determine two resistors, series and depletion layer resistors. So this blue line stands for absolute value of imaginary component. And why do we take absolute value? Because it actually negative value. And any suggestions why it's negative? So we made it positive in order to plot in semi-log scale, because you cannot plot negative values in semi-log scale, but this imaginary component is negative. What is impedance of electrical circuit? It is square root of R square plus omega L minus 1 over omega C square. So you see that because of phase shift between voltage drop over inductor and capacitor, we have here plus and here minus. So when we consider about phase shift between current and voltage, so we have this minus next to contribution of of a capacitive reactance. So this, since we have a capacitor here, this is our capacitor, so we have negative value for imaginary part of impedance, because if we show it in complex form, so it will be active resistor plus I times omega L minus unity divided by omega C. So that is Z prime, and this is Z double prime. Since we have not inductor, but we have capacitor, this is 0, and we have minus 1 omega C. So that's actually negative. That's why the Z double prime, imaginary component of impedance, is negative. So we take absolute value and plot. So we have some curve with maximum, and this maximum, first of all, it gives us half of depletion layer capacitance, the value, magnitude of this maximum, and its frequency position, we go down, gives us 1 over RD times CD, which is time constant of this parallel capacitor and resistor. Time constant is product of resistor and capacitor. Shows how fast we can discharge capacitor via this resistor. So we can, from this position and magnitude of this peak of imaginary component of impedance, already determine quite like all parameters of this circuit. So that's explanation of this impedance. And as I said, admittance is 1 over impedance. So we need to we determine admittance as 1 divided by Z prime plus I Z double prime. As a result, we get these two components. We have real component of admittance, which is equal to G, and we have imaginary component of impedance, which stands for B, susceptance. So now we can measure impedance. So there is impedance analyzer which gives us Z prime and Z double prime as a function of frequency. So we measure these guys, Z prime and Z double prime. We know that minus Z double prime divided by Z prime square plus Z double prime square should be equal to susceptance. And we know from here that capacitance, which we are interested in, should be susceptance divided by omega. Means minus 1 over omega times Z double prime divided by Z prime square plus Z double prime square. So this minus we have here, and keep in mind that this guy is also negative. Z double prime is negative, so eventually it will give us positive value, and that should be our capacitor. However, if we substitute for Z prime, Z double, and Z double prime these expressions in terms of parameters of the equivalent electric circuit, eventually we will get CD, the capacitance of the depletion layer, which we want, that's what we want, times some not so simple function of resistance, of depletion layer, series resistance, and frequency. So everything, and capacitance, actually. Here it's also there. So we have quite complex function with different variables. Moreover, it depends on frequency. And instead of just getting a number, we get some massive frequency dependent function. So that's where the problems come, and unfortunately in the field people quite often do not take appropriate approach for measuring depletion layer capacitance. They just measure it at certain frequency and provide the value. That is a mistake, because it actually not just a value, but some frequency dependent function. So that's how it looks. Here we plot this C, which we actually calculate with that function, which we should consider, divided by real depletion layer capacitance. So that's what we want to know. But we measure this C, and CD is what we want. So we have the ratio between them as a function of frequency. And now I simulated this for you guys with different values of series resistance. So we have 10 ohm, 50 and 100 ohm of series resistance. And we see that for 100 ohm, it's relatively high series resistance, but still quite normal. We have a very strong frequency dependence of this ratio. So we want to be in this range of unity, because we want this measured C be equal to CD. So the ratio between them should be unity. But we see that at high frequencies, it actually very far from unity. It goes down quite a lot. Even 50 or 10, it also deviates from unity. So in the high frequency region, the value, what we get for depletion layer capacitance from our measurements is not real, because it is goes way in different direction than it's supposed to be. So you would probably ask, okay, what about this region? Here it's unity, means the measured will be depletion layer capacitance, but this is true only for low frequency region. And if we have ideal PN junction with no defects and specifically with no interface defects between materials and contact, that could work if we have reverse bias. So when we have reverse bias and when we don't inject charge carriers in this semiconductor, it could work. But the thing is that even for ideal PN junction, when we have forward bias and we start to inject charge carriers, I mentioned about this diffusion capacitance. These charge carriers, it takes some time for them to respond to electric field, be injected and extracted. And that's why they respond to low frequencies. So at low frequencies, we will get some parasitic effects of charging defect, decharging, discharging defects, injecting, extracting charge carriers. And that's why what we measure, we get a lot of parasitic effects in real life at low frequencies. So because injection, extraction happens even in ideal device, and life is not real, the reality is not ideal, and that's why we need to also take into account some defects and impurities, which can be charged and discharged in the process of applying AC voltage to the system. And eventually we have issue with parasitic capacitance, which we measure. So we want, usually, those who take care about their measurements want to go into high frequency region where all these processes happen too slow in order to follow the AC signal and contribute to measured capacitance. So that's why we want to do our measurements somewhere here, starting from like already in close to 1 megahertz and higher, in order to avoid all parasitic effects. But in this region where we don't have parasitic effects, we have this effect of series resistance, and that messes things up. So how we can deal with this? It actually has a very simple and straightforward solution. So if this resistor is a problem for us, we can subtract it. So it's here in the active component of impedance. So if we subtract this resistor, so we again simulated here how real component of impedance depends on frequency with black line and without series resistance when we correct for it. So that's what we saw previously. It saturates at this high frequency region. But if we subtract this, and we know what to subtract because we measure this real part of the impedance as frequency dependence. We see where it saturates. We extrapolate this saturated region to the interception with the impedance axis, and we get value for this series resistance. So we know what to subtract. We subtract it, and now we get this further decline of real component of impedance. Once we do this, we go from real, which includes this series resistance, to kind of corrected, already ideal equivalent circuit, where we have only capacitor, which we're interested in, and a resistor connected in parallel. So once, instead of having just Z prime, we put here minus RS for Z prime, we do this correction and we get corrected capacitance. We indeed get the capacitance of the depletion region, and that will be correct because we can do this at high frequency region. We kind of terminate all possible parasitic effects since we are working in the high frequency region, and we do this correction for the series resistance effect at high frequency measurements, and indeed get the correct value of depletion layer capacitance. So by the way, you can actually practice in some calculations. So this like final, for instance, this final equation, you can substitute here instead of Z prime this, and instead of Z double prime these equations. So eventually you indeed can show that we will get diffusion capacitance, not some diffusion capacitance multiplied by some weird function. So this is the list of questions you guys need to know and understand about formation of p-n junctions. That's very important. I highlight this, and I mentioned before and now mention that understanding of p-n junction formation and its basic characteristics is the key for your understanding of semiconductor devices. So that is very important. So if you have any questions, you're welcome. I think I'm done for today with our discussion of p-n junction formation. So we will continue next week with the derivation of equations for, like, analytical derivation of equations for current voltage characteristic, because so far we considered how we form, how electric space charge distribution, electric field electrostatic potential, band bending, thickness of the depletion layer, capacitance of the depletion layer in terms of its voltage dependence, and also what we can extract from this voltage dependence of capacitance. And also at the end, quite important moment, we discussed in details how correctly measure this depletion capacitance. So now you know quite a lot about p-n junction, but most common application is rectification, like rectifier. It's a diode based on p-n junction. So we obviously need to quantitatively analyze current voltage characteristic of a p-n junction. That we will start doing next lecture. Okay, thank you very much for attention, and see you next time. Bye bye.